equivalent circuit of transformer. We have drawn the diagram of transformer. Similarly, we draw the transformer diagram. This diagram can be converted into its equivalent circuit. The transformer have primary resistances, reactances, secondary resistance, reactances. Its equivalent circuit would be first represent these two windings. Primary winding, secondary winding. You can say you draw the transformer like an ideal transformer. Now, thereafter, your transformer draws no load current I naught, which is having active component, let it be represented by R naught, and magnetizing component X naught. Let this be the magnetizing current, this be the working component. Further, your primary winding is having resistances and reactances R1, X1, and this will be the applied voltage V1, and this will be the induced EMF E1. And secondary side is represented by R2 and X2. This here load, let load impedance be Z, where ZL be RL plus JXL, RL plus minus JXL. This will be the terminal voltage V2, this will be the E2. This will be the equivalent circuit of the transformer, in which we have represented all the transformer parameters with the diagrams. And let N1 be the number of turns in the primary, N2 be the secondary. And we know, or from here, E1 by E2 is N21 by N1 is K, that is the transformation ratio or turn ratio. Now, if you want to solve this circuit or simplify, or you find out the parameters, or you want to find out the current, so it will become difficult if you keep these parameters on the either side. So you can, on the both sides, you can transfer these parameters on either sides so that you can simplify or to solve the circuit. So let us transfer these parameters on the primary side. These resistances and reactances. As we see here, if you want to find out IM, so this EMF is in parallel with this, so it will be E1 by X naught, IW E1 by R naught, and your Z1 R1 plus JX1, and your impedance, secondary side impedance is R2 plus JX2, and your Z naught would be both these resistances and reactances is in parallel. So this can be represented by 1 by admittance, and this admittance can be find out conductance, susceptance, G plus G. So these are the different side impedances and reactances. Now, if we transfer these parameters on the either side, for example, we are transferring it, so what would be its equivalent value? Let us transfer this circuit on the primary side. This is E1, R2 dash, X2 dash, ZL dash, and that would be equal to ZL by K square. We have already discussed how we can transfer parameters on the either sides. And your R2 would be, dash would be R2 by K square, and X2 by K square. And the voltage on this side would be E2 dash, and that will be equal to E2. Likewise, your corresponding voltage would be V2 dash on this side. Now, you can find out the total impedance of the circuit. What will be the primary impedance? Z1. It will be total impedance. Z will be Z1, and this Z2 and ZL dash are connected in series in parallel with Z0, or this can be represented by, in place of Z0 we can represent it by ZM. Now, this will be Z1 plus Zm in parallel with Z2 dash plus ZL dash, or impedance would be Z1 plus ZL, Z2 dash, ZL dash, Z2, ZL plus Z2 dash plus ZL dash, and your V1 is I1 Z1, and we can find out the primary current easily. This circuit can be further simplified if we shift this no load parameter on this side. that would not affect the result largely. So for simplification purpose, we just R1 X1. Now, what will be the total impedance? Zm in parallel with Zm in parallel with Z1 plus Z2 dash plus Zn dash, or Zn Z1 plus Z2 dash plus Zn dash, or this will be Zm plus Z1 . So in this way we can simplify the network and solve the network. Similarly, we can transfer these parameters on the secondary side. So this will be the approximate equivalent circuit of the transformer. We have shifted from actual, we convert this diagram into the actual circuit, equivalent circuit, and for our calculation purpose or simplification purpose, this can be simplified like this. Losses in transformer. Transformer is a static device, that's why no mechanical loss. Generally, losses are classified in core loss, copper loss. Core losses are the further segregated as hysteresis and eddy current losses. And copper losses are the winding losses. That is your current in primary winding plus current in secondary winding. Your whenever a magnetic material is subjected to the cycle of magnetization and demagnetization, certain power would be required, and that power required or that power consumed is hysteresis loss. Means we should select a magnetic material having minimum hysteresis group area, and your hysteresis losses pH may be represented by certain hysteresis constant Kh, maximum flux density 1.6, F frequency that remains more constant, and V is the volume of the iron core. When this magnetic material is placed in the magnetic field, certain eddy currents circulates in the core, and these eddy currents induces the EMF in the core. Hence there is power loss, and may be given by Bm square F T square, and unit is in watts, where V is the maximum flux density, F is the frequency, K is the eddy current constant, and T is the thickness of the lamination. These losses may be in winding losses, primary winding copper losses, secondary winding copper losses are the total copper loss. or they may be represented as total equivalent resistance referring to the secondary, primary, or total equivalent I2 square, total or equivalent resistance referring to secondary. So these losses can be find out by certain test on the transformer. For example, we can find the core losses using open circuit test. First, we can find these core losses using open circuit test. In open circuit test, we have two windings of the transformer. One thing is clear, one side is kept open. So we have kept one side open. So generally we kept high voltage side open and apparatus is being connected on low voltage side. To measure the losses, let us connect an wattmeter with it to measure no load current, ammeter, and voltmeter to measure the voltage. And rated voltage is applied across the low voltage side. We can perform this test on either side. At high voltage side we can replace it, low voltage side can be kept open circuit. We can apply the voltage on high voltage side, but we have to apply the rated voltage. For example, you have a 11 kV oblique 0.4 kV transformer, 11 oblique 0.4 kV transformer. So it will be easier to apply a 400 volt in place of 11,000 volt in the testing. That's why, because you would require a arrangement to measure the voltage of 11 kV. If you perform this test on high voltage side, you would require the wattmeter with a rating of 11 kV, or you have to connect certain current transformer, potential transformer to reduce up the rating. Then, in place of, if you apply this test is performed on low voltage, the equipment ratings becomes lesser. That's why this test is being performed on low voltage side. At rated voltage you apply. As secondary side is open circuited, the current in the drawn from the supply will be the no load current, which will magnetize the core and supply to no load copper losses and core losses. As the current is very low, it may be 2 to 5% of the rated current, so we can neglect the copper losses, and this wattmeter will give the reading of your iron losses. That's why we have got this wattmeter, that if this would measure the voltage of V1, so this will be V1 I naught cos of phi naught. So this wattmeter will be the core losses if no load copper losses are neglected. So we can find out the core losses, or your IM is I naught cos of phi naught, this because this current supplied for magnetizing as well as working component. This is sine of phi naught. I naught cos of phi naught. And this magnetizing component Im is V1 by R naught, X naught, and IW is V1 by R naught. In this way, we can find out the value of R naught and X naught also. We can find out the no load parameters of the transformer, because V1 is known, I naught is known. From this wattmeter reading, you can find out the cos phi naught. When cos phi naught is known, so you can find out Im and IW. And Im and IW are known, we can find out X naught will be V1 by Im and R naught will be V1 by IW. So using this particular test, we can find out the core lossage of the transformer, that is your hysteresis and eddy current lossage. Now we have to find out the winding lossage. If your resistances are not known, then you can directly find out the copper lossage using short circuit test. This short circuit test is being used to find out the copper lossage of the transformer and to find out the parameter of your transformer. Difference is that this test is being performed at high voltage side at rated current. For example, this test is being performed on the primary side. So I1 is the rated current. Now the voltage applied would be short circuit voltage of that voltage, and this low voltage side is short circuit. We will apply a certain voltage which would circulate the rated current. It may be 5% or 2 to 5% of the rated voltage. That's why this test is being performed on the high voltage side, because current is rated and rated current is low at high voltage side in comparison to low voltage side, and the voltage applied would be very low. That's why we can apply on this test on the high voltage side. We can perform on the low voltage side. The problem becomes same, that is the rating of your apparatuses, because wattmeter rating, accordingly you have to current CTs, PTs to measure the power with help of this standard wattmeter. That's why this test is being performed on high voltage side, and this wattmeter will give the reading of copper losses, because the voltage is low, so your magnetization of the core would be low. Hence, your eddy current and hysteresis losses would be low. So whatever losses will be losses due to the circulation of rated current in the winding. That's why if your low voltage hysteresis and eddy current losses are neglected, this wattmeter will give the reading of copper losses. Means this wattmeter will give the reading of I1 square equivalent resistance referring to primary side, or maybe secondary side is this side, equivalent resistance referring to secondary side. Wattmeter reading is known, rated current is known, you can find out the equivalent resistance on the either side. Likewise, from these readings, Z1 will be short circuit voltage divided by V by I. That will be the impedance, equivalent impedance referring to primary. As we know the equivalent impedance referring to primary and equivalent resistance referring to primary, we can find out the reactance referring to primary. In this way, we can find out the parameters of the transformers and copper losses of the transformer using short circuit. Once you are aware about the copper losses and core losses of the transformer, you can find out the efficiency of the transformer. Efficiency of the transformer. We have measured iron losses or core losses using open circuit test, and we have measured copper losses using short circuit test. Once these losses are known, we can find out the efficiency. Simply, efficiency is the ratio of output power divided by input power. Or and if you want to find out the efficiency in percentage, this can be written as 100%. Or this may be written as input output divided by output plus losses. Losses are your copper losses, iron losses. Iron losses are constant and copper losses are variable losses. They are dependent upon current. I1 square R naught 1 or I2 square R naught 2 into 100. And these, or we can write it as input minus losses divided by input, that is now in case of transformer, what is output power? This is output is V2 I2 cos of phi 2. Input is V1 I1 cos of phi 1. Losses are copper losses, iron losses, and generally the unit of both should be same, that is in watts, or you can take in kilowatt, numerator and denominator. It should be same. And we will take these parameters in terms of watt or kilowatt, not in terms of kVA. Where transformer rating is given in terms of kVA, as its iron losses are dependent upon voltage and your copper losses are dependent upon your current. But we will find the efficiency or efficiency determined using rating in kilowatt. Means your kVA rating is being multiplied with power factor of the circuit. If you are taking input, so V1 I1 is the apparent power, that is the kVA rating. VA rating is volt ampere rating is volt ampere rating, and cos phi 1 is the power factor at the primary side. Cos phi is the power factor at the secondary side. So here your equation, for example, for this case, efficiency would be equal to V1 I1 cos of phi 1 minus I1 square R naught 1 are your copper lossage minus iron lossage divided by V1 I1 cos of phi. Your efficiency would be maximum when V by di would be minimum. So differentiate this equation with respect to I1. For maximum efficiency, this should be with differentiate with respect to I1 should be equal to 0. So we can differentiate it, or we can write it as first further simplify it 1 minus I1 R naught 1 V1 cos of phi 1 minus V1 I1 cos of phi. Now you differentiate. Differentiation of 1 is 0 minus I1, differentiation of I1 R naught 1 is R naught 1 by V1 cos of phi 1, and differentiation of this would be plus V1 I1 square cos of phi 1. And your efficiency would be maximum when this should be equal to 0. Therefore, your V1 I1 square cos of phi 1 should be equal to R naught V1 cos of phi 1. Or this would cancel. I is I1 square R naught 1. That is your iron loss is equal to copper loss. So when your iron lossage would be equal to the copper lossage, efficiency of the transformer would be maximum. And what would be the maximum current? Maximum current would be, or the current at which the efficiency would be maximum, R naught 1 or I1 square is this one, or Wi should be I2 square R naught 2, and I2 should be current at which efficiency would be maximum. So we can find out the current at which efficiency would be maximum, and this would be the condition for maximum efficiency. So we can derive this condition on the either sides. From this, one thing is clear: current at which efficiency is maximum is this one, and if we write down the formula for the efficiency, it would be output by output plus losses, or V2 I2 cos of phi 2, V2 I2 cos of phi 2, I2 square R naught 2 copper losses. We can find out the efficiency at any load. For example, load is 50%. So, into 100 percentage efficiency. So this X is the load factor. And load factor for maximum or full load, X is 1 at full load. For example, load factor is 0.5. So this formula becomes X because your copper losses are also dependent upon load. If your load becomes 5, means half, so its losses becomes 1/4. It is 0.75, accordingly losses would change. It means if we say that the load factor 50% load is connected, what it means? Value of X is 0.5. 75% load is connected, 0.75. 125% load is connected, 1.25. Load factor is this one. So this will be the formula by which we can find out the efficiency of the transformer. Or this can be further represented as X kVA into load kVA into power factor. X kVA into power factor into copper losses, iron losses, where copper losses are Xi2 square R naught 2. That depends upon the load factor, and percentage of efficiency would be multiplied with 100. So we can find out the efficiency at n. If the input your rating on the primary side is given, this is the rating of the transformer. You can say rating of transformer. This is the power factor of the secondary side, load power factor. Load power factor. This is the rating of transformer. And this is the what is the load connected with the transformer. Auto transformer. Generally, your auto transformer is used for low voltage low power ratings, and generally used for the power booster, or where we require the low voltage for starting the electric motors. So these transformers are being used in these applications, and they are different from two winding transformer, because in two winding transformer we have the electric separation, whereas in case of auto transformer we have only one winding, and that winding is being used to step up or step down the voltage. Basically, this transformer is a one winding transformer and works on the principle of self induction. For example, we want to step down the voltage, so this will be the input voltage V1, and this is the load connected. this will be divided into three parts, A, B, C. Now current in this part of winding is current is I1 and load current is I2. So this is the step down transfer, but obvious this current is I2 and this one is I1. On the low voltage side, current would be higher in comparison to high voltage side. Direction of current or current in this portion of the winding would be I2 minus I1. This will be the current flow in this portion of winding, I1 will flow in this portion of the winding, and I2 is the load current. Number of the turns on the primary side is considered to be N1. So here N1 is AC. And number of turns on the secondary side is your secondary side is BC. Let it be N2. Number of turns in that. If the same transformer is being used to step up, just change it. This is the input V1, this is the input current I1, and this is the output, and load is being connected. I2, again A, B, C. So this current is I2, this current would be I2. This side current is higher than secondary side current in case of step up transformer. So this direction of current in this portion would be I1 minus I2, and this current would be I2. So using this auto transformer, we can step up or step down the voltage. We can vary the voltage. If this point is we are able to make this point variable, slip over it, so we can have the voltage as per our requirement. So this basically this transformer may be used for lab application purpose. It may be for distribution line. It may be used for voltage booster. It may be used to give the reduced voltage starting. For example, in your electrical machines, you require 50% voltage or 60% voltage so that the starting current would be low. So you can use this transformer for that purpose. In power applications, generally, we rarely use this transformer. These are the just used for the applicability. Another problem with this auto transformer, it didn't have electrical separations. Because same winding, it is electrically connected. Now, only difference of the induced EMF is works on the principle of self-induction, means E2 would be N2 by N2 d phi by dt, and E1 would be N1 d phi by dt, means the induced EMF will depends upon the number of turns, and if the primary side number of turns are more, so it will be on secondary side number of turns are we have considered less, so it will step down and accordingly step up transformer. Advantage of the transformer in comparison to two winding transformer that it has only one winding, but obviously in case of two winding more winding copper is required, so it would have the saving of the copper. So how much copper we can save in case of auto transformer in comparison to two winding transformer. So let us discuss saving of the copper. Let us consider this step down transformer. Your copper depends upon the weight of the copper depends upon the length of the conductors, and length depends upon the number of turns. And your Cross-sectional area of the conductor depends upon the current. If the current is higher, the cross-sectional area would be more. If the current is lesser, it would be lesser. So means weight of copper is directly proportional to number of turns and current flowing. So now let us see in this particular case what is the weight of the copper in case of auto transformer. Weight of copper in auto transformer. That will be WA. Yes. This portion, weight of this portion, AB, and what is this AB? Length of this AB. Total number of turns are N1 minus N2. So in this portion, current N1 minus N2. This is the weight of the copper of this portion AB. What is the weight of the copper of the portion BC? In this portion, number of turns are N2 and current is this one. Plus N2 I2 minus I1. Now, weight of the copper in case of ordinary transformer or in a two-winding transformer, proportional. Weight of the copper of the primary winding N1 I1, number of turns in the primary winding and current in the primary winding, plus weight of the copper of the secondary winding. That depends upon the number of turns of the secondary winding and current in the secondary winding. Now, if we divide these, the ratio of weight of copper in auto transformer WA divided by weight of copper in ordinary transformer, that it will WO denoted by. It would be auto transformer I1 N1 minus N2 plus N2 N1 I1 plus N2 I2. Now we simplify it. So this WA by WO would be equal to I1 N1 minus I1 N1 I1 minus N2 I1, this one, plus N2 I2 minus N2 I1 divided by N1 I1 plus N2 I2. N2 I1, it will be minus 2 N2 I1. Divide numerator and denominator by N1 I1. But you will have 1 minus 2 N2 I1 N1 I1 plus N2 I2 N1 I1 divided by N1 I1 1 N2 I2 N1 I2. Now ordinary transformer N2 by N1 is K, and this will be cancelled. So 1 minus 2K. N2 by N1 is K. I2 by I1. N2 by N1 K. I1 by I2 is K. So this will be K by K plus 1. Now 1 plus K by K, that is equal to 1. So it will be 1 minus K divided by 2. Or weight of auto transformer will be 1 minus K weight of ordinary transformer. Now what would be the saving of the copper? That is weight of ordinary transformer minus weight of auto transformer. And that will be equal to saving copper in case of ordinary transformer, weight of copper minus weight of copper in auto transformer, that is 1 minus K of ordinary transformer, and weight of ordinary transformer 1 minus 1 plus K. Cancel. So saving of copper it will be equal to weight of ordinary transformer. For example, you requires transformation ratio 1. 1 by 1. No winding is required. You can directly connect it. It is 0.5. Transformation ratio is 0.5. And 5 of ordinary means 50% copper saving is there, and so by this we can save the copper, but problem is that no electrical isolation is there. That's why we generally use this transformer for applications only, for the low rating applications like practicals, like starting of motors, like boost up the voltage. We can use the auto transformer.